Hi everyone, welcome to part 2 of OCR AS Chemistry June 2024 Paper 1. If you do find this video useful, please do give it a like and subscribe. Question 22 is about the reactions of acids. What is the difference between a strong and a weak acid? Strong acids completely dissociate, whereas weak acids partially dissociate. Part B is ethanoic acid is found in some descalers to soften hard water. Student carries out a titration with a standard solution of sodium carbonate to determine the percentage composition by mass of ethanoic acid in a descaler. The equation is shown below. The method is outlined below. So dissolve 6.5 grams of the descaler in distilled water, transfer the solution to a 250 volumetric flask, make up to the mark with distilled water and invert several times. Pipette 25 centimeters cubed of this solution into a conical flask and add a few drops of indicator. Titrate the solution with 0.2 moles per decimeter cubed of sodium carbonate in the burette. Student carries out a trial titration followed by further titrations. The results are shown in the table below. The trial titration has been omitted. So you just have to complete the table by subtracting both values. So 4.95 subtracted by 24.55 is 24.4. Now make sure you add the 0 so you stay consistent with the two decimal places. The next one's 24.15 and finally 24.25. Calculate the mean titer to the nearest 0.05 centimeters cubed that the student should have used. So mean titer, we only use a concordant result, which seem to be these two, as they are 0.05 of each other. So that's the middle value between the two would be 24.20. That's the mean titer, 24.20. The next question is to calculate the percentage composition by mass of ethanoic acid in the descaler. Assume that ethanoic acid is the only acid in the descaler. Give your answer to 3 significant figures. Okay, so looking at the information we have, we've just worked out the mean titer for the sodium carbonate, and we know the concentration of it, which means that we could calculate its moles. So moles of sodium carbonate would be equal to 0.2, which was its concentration, multiplied by 24.2, divided by 1,000 to convert that to decimeters cubed, and that is 4.84 times 10 to the negative 3. Now, we could use the moles to calculate the moles of ethanoic acid using the molar ratio. So it looks like the molar ratio is 1 to 2, so the moles of ethanoic acid is going to be twice that, but this would be in the 25 centimeters cubed that was pipetted. The original was 250, so once we find the moles by dividing by 2, we'd have to multiply by 10, so we know the moles in 250. And once we have the moles, we could calculate its mass using the MR, and then we can work out the percentage by the total mass, which was 6.5. So then the moles of the ethanoic acid, now this would be in 25 centimeters cubed, would be twice this because it's a 2 to 1 ratio. So 4.84 times 10 to the negative 3 times by 2. That is equal to 9.68 times 10 to the negative 3. Then we can multiply this by 10, and this would give us in 250, the moles in 250 centimeters cubed. So times by 10, that would be 9.68 times 10 to the negative 2. Then we could use a small value to calculate its mass. So mass would be equal to mole multiplied by the MR. So the mole we know is 9.68 times 10 to the negative 2, multiplied by ethanoic acid, so that's CH315 and COOH, so plus 12, about 60, I believe. And that would equal to about 5.808 grams. Then percentage by mass is this divided by the total mass, which was 6.5. So percentage is 5.808 divided by 6.5, and that is times 100, and that would be equal to 89.3538%. Decimal places, okay, it says 3 significant figures, so that's 89.4% as the answer. Question 23 is about covalent compounds of nitrogen. Ammonia is manufactured by reacting nitrogen and hydrogen gases. This is a reversible reaction, and the equilibrium is shown below. This is an example of a dynamic equilibrium. State 2 features of a dynamic equilibrium, so the rate of forwards and reverse reactions or backwards reactions are the same or equal. The second thing is that this occurs in a closed system. That's another point, occurs in a closed system. And a third possible point that you could have made is that the concentrations of the reactants and the products stay relatively constant. So concentrations of reactants and products are constant. Right then, part 2 is to state and explain the conditions of temperature and pressure that would produce a large equilibrium yield of ammonia. So if we look at this equilibrium, we see that the enthalpy, or delta H, is negative. This tells us it's exothermic. So if something's exothermic, it gives off heat in the products, right? The products release heat. So you could say that this side is quote-unquote hot. The other side, the opposite side, would have to be the opposite, which is cooler. Okay? Right, so if we were to increase temperature, it wants to do the opposite. That's what Le Chatelier's principle is. The opposite would be reverse to the cooler side. Now, that is not ideal because we need to produce a large yield of ammonia. So in this case, you'd want to decrease temperature, and by decreasing temperature, the equilibrium will shift towards the right-hand side, meaning the exothermic side, to sort of recalibrate it, if you want to say it that way. So basically increasing temperature of the system because the forward reaction is exothermic. Then in terms of pressure, now the standard statement for pressure is that increasing pressure shifts it to the side with fewer moles. Now if we look at the side with fewer moles, it would have to be the product side because you've only got 2 moles of gas over here, whereas 3 and 1, so 4 moles of gas on the reactant side. So in this case, a high pressure would be favorable, as this would shift equilibrium to the side with fewer gas moles, which in this case is the right-hand side or the product side. So this is the answer, and I've numbered out how you get the marks for it. So it's 1 mark for what you do to temperature, another mark for what you do to pressure, and the third mark overall is explaining how that affects the system. So if you only explain the temperature thing but not pressure, you automatically lose that third mark. So the third mark is you have to get both explanations down. The next question is part B, which is hydrazine, as shown below, is used as rocket fuel. As a fuel, it reacts with oxygen, as shown below. The average bond enthalpies are shown in the table. Calculate the average bond enthalpy of the NH bond. Alright, so they've done us a favor by drawing it out, so this should not be too difficult. So the way you can work out enthalpy is it's bonds broken subtracted by bonds made. So our delta H value is negative 581, and that's bonds broken, meaning the reactants. The bonds made are the products. So the reactant bonds that we are breaking is one NN bond, so that is 158, plus 4 NH bonds, but we need to work that out, so that's basically our 4x, plus the oxygen. We've got 1 molecule of oxygen, 1 double bond, so that's 498. Subtracted by the bonds made, so we've got N2, which is 945, plus water. Now you've got 2 molecules of water, so that's a total of 4 OH bonds that are being broken. So that becomes 4 times 464. Alright, so if you put this in your calculator, it should look something like this. So 581 is equal to 4x subtracted by 2145. And then x would be equal to 1,564 divided by 4. And that is 391. And bond enthalpy is always endothermic because you're putting in energy to break a bond. So that's 391, positive 391 as the answer. Quick note is that this positive sign was not quite required. It's in brackets on the mark scheme, but it's just good for you to keep in mind that it should have been a positive number. Alright, part C is hydrogen cyanide, HCN, is bonded by a single bond between H and C atoms and a triple bond between C and N. So that would mean, so like H, single bond, and then triple bond to CN. Draw a dot and cross diagram for a molecule of HCN. Use different symbols for electrons from hydrogen, carbon, and nitrogen. So let's say hydrogen is circles or dots. Carbon, we could put crosses, and for nitrogen, let's say triangles. It could be anything as long as it's different. Right, so we know that hydrogen forms a single bond with the carbon, so a dot and a cross, and then carbon to nitrogen's triple bond. Now we know that carbon is in group 4, yeah. Okay, so it's in group 4. That means each of the 3 remaining electrons is participating in the triple bond. And like we said, triangles for the nitrogen, and it has to be alternating, so 1 cross 1 triangle, so forth and so on. Now, nitrogen, I believe, is in group 5. Group 5, so that means 5 electrons in the outer shell. So there's 2 triangles that we need to draw. Okay, that looks ugly. 2 triangles as such. Right, question 24 is about hydrocarbons. The skeletal formula and boiling points of 3 isomers are shown in the table. State and explain the trend in boiling points shown in the table. So it looks like the boiling points are decreasing, and they're decreasing, or the trend we could see with them decreasing is this, which is branching. So as branching increases, the boiling point decreases. What is the explanation for this? Well, this is due to surface contact. So if I just draw another of C6H14, alright, so these molecules, you see how they're like puzzle pieces and they can sort of stick close together? That sticking close togetherness is what is known as surface contact. Surface contact is basically lots of intermolecular forces or London forces forming between them. And the more surface contact means more intermolecular forces, which results in more energy being needed to break those intermolecular forces, resulting in a higher boiling point. Whereas if there is branching, I hope you can see now that the two molecules, so like if I had another one of these, they cannot sit as closely together as the top one, and that would decrease the surface contact between the two, which means fewer intermolecular forces, therefore requiring less energy to break. So this is the answer. Each bullet point is worth 1 mark, so a total of 4 marks. Now, if I'm being honest, the last point, I would have worded it slightly differently, but this was exactly what's on the mark scheme. Instead, I would say that, just a converse argument really, where less energy is needed to break intermolecular forces with less surface contact. Okay, that brings us to question B, which is hydrocarbon C2H6 reacts with bromine to form C2H5Br under suitable conditions. Complete the table to show the mechanism for the 3 stages of the reaction. With Br2 to form C2H5Br, the equation for one possible reaction for termination has been completed. In your equations, use molecular formulae and dots with any radicals. So this is free radical substitution, that's the mechanism for this. And the conditions required for the initiation step is UV light. The equation is where a bromine molecule becomes 2 bromine radicals. And this happens due to homolytic fission. So just quickly, some side notes is here's a bromine molecule, and in the presence of UV, each bonding electron goes to each of the bonded atoms. Right, so these are fishhook arrows to show only one electron being transferred. And again, this is homolytic fission. Right, that's besides the point. Point is the next question, which is the propagation step. This is when one bromine radical reacts with the compound in question, which is C2H6, and this will always form an organic radical. Just that's the rule, is that the first step of propagation forms an organic radical. So what I mean by that is the organic radical formed is C2H5 radical. So it kicks off one of the hydrogens, or rather the Br radical steals one of the hydrogens to form HBr. And because this is a chain reaction, the organic radical will react with more bromine molecules to form more bromine radicals and the compound, which is C2H5Br, so the desired compound required. And this step the propagation step keeps going over and over again until you run out of the reactant. Reactant would be either one of them, so either the bromine or the C2H6. And then comes the termination step, and in termination, all of the radicals combine together. So one possible combination is 2 bromine radicals combining. Another combination could be a bromine radical and an organic radical, so C2H5 coming together to make the desired product. And you could also have C2H5, so 2 organic radicals coming together. And that would make C4H10. Part C is propene has different bond angles and shapes around the carbon atoms. The displayed formula of propene molecule is shown below. Predict the bond angles and the names of the shapes around carbons 1 and 2 above, and explain why the bond angles and shapes are different. So carbon 1, surrounding it, we can see 4 bonding regions, which means tetrahedral, with a bond angle of 109.5. The next one is 3 bonding regions. You've got 1 double bond, 1 and 2 single bonds, so that would make it trigonal planar, with a bond angle of 120 degrees. For the explanation, it's simply that the bonding pairs repel as much as possible, which gives it the shape. So these are the points required to score the 5 marks. It's 1 mark for carbon 1 and carbon 2, and then 3 marks for the explanation. Each bullet point is worth 1 mark. Question 25 is 3 alcohols, A, B, and C, are structural isomers with the molecular formula C5H12O. A, B, and C take part in combustion reactions. Complete the equation for the combustion of this alcohol. So it looks at complete combustion, which means plentiful oxygen supply to make carbon dioxide and water. Right, so we could balance the carbons first, 5 over here, then for the hydrogens, 6, and then lastly leaving us with oxygens. So that's 16 oxygens on the right-hand side, and we already have 1 oxygen for the alcohol, so we just need 15 more. And we have an O2, so we could find half of 15, about 7.5, I believe, so 7.5, and that would balance it. So we've got 14 from here, plus the extra 1 oxygen from the alcohol. Now, whenever it comes to balancing alcohols, I see, funnily enough, many students getting this wrong because they forget the oxygen in the alcohol, so please be mindful of that when balancing. Right, alcohols A, B, and C are each reflux with acidified dichromate. The organic products are shown in the table. Complete the table to show the structures of alcohols A, B, and C. So this one over here looks to make a carboxylic acid, so it would have to be a primary alcohol. So the primary alcohol that would make this would look as such. So just to confirm, that's 5 carbons, that's 1, 2, 3, 4, 5, yeah, that checks out. The one below looks like a ketone, so it'd have to be a secondary alcohol, so the OH would be here. Counting carbons again, that's 1, 2, 3, 4, 5. That works as well. No reaction would make it a tertiary alcohol. So we could stick that where the methyl group is. So that's 1, that's OH. The second carbon, third, fourth, and fifth. Yeah, so that would be the answer to this question. Draw a label diagram to show how you'd set up for distillation. So distillation's with the condenser sideways. Now please excuse my drawing not very good at it, but okay, so that's a round bottom flask, or pear-shaped flask. Pear-shaped or round bottom flask. That's what this is. Then you've got the tube. Alright, and then that's the condenser going sideways. Oh. Then you can put the thermometer up over here. You only leave the top open if it's a reflux setup, because then that would build pressure, but if it's distillation, thermometer could be at the top. And that would collect in a beaker. Right, now this is the important part, which is the water jacket. So the water jacket must be drawn in such a way that water out is at the top and water in at the bottom. So water out at the top and water in at the bottom. Okay, something like that should have been the answer. And before I forget, the heat source is coming from the bottom over here. I think that should be all. Actually, there's one more label, which is this. That's the condenser. Okay. Question D is alcohols can be prepared by the hydrolysis of haloalkanes with aqueous alkali. Write the equation for the hydrolysis of 2-bromo-2-methylpropane. Show the organic compounds as structures. So I'm assuming you could do displayed formula for this. To stay on the safe side, I believe structural should have been fine, or even skeletal formula. So propane would be 3 carbons. Middle carbon has a bromine and a methyl group. Okay, so this looks like structural, but displayed or skeletal should have also been fine. Plus water, because it's hydrolysis reaction, to give you actually, not water, because it says aqueous alkali. That would indicate OH minus present. Despite it being hydrolysis, you would assume water, but it's OH minus because of the aqueous alkali statement. Right, so then this would swap out the bromine for an OH. That's just nucleophilic substitution, leaving us with a Br minus. Now, not HBr, again, because it's aqueous alkali condition. If the question did not state this, you could have used water and HBr accordingly, but it doesn't, so this would be the correct reaction. Part 2 is a student hydrolyzes chloroalkane, RCl, a bromoalkane, RBr, and a chloroalkane, RI. For a fair comparison, the student has chosen the same R group for each haloalkane. Predict, with reason, the relative rates of hydrolysis of these 3 haloalkanes. So relative rates of hydrolysis, the fastest reaction would be the iodoalkane, because the CI bond enthalpy is the lowest. So lowest bond enthalpy means less energy needed to break the bond, therefore faster the reaction. So the fastest and the slowest rates, so if we put that, it would be RI, the next fastest is RBR, the next fastest, or the least fastest one is RCl. Reason being that's carbon. The carbon-iodine bond is the weakest. And because it's the weakest, least energy must be put in to break it, making it the fastest to hydrolyze. This would be followed by CBr, and then finally CCl, bond-wise. Okay, right, that is it for this question paper. I hope you found it useful. If you do have any questions, feel free to put them in the comments below. I'll try to address every single one. Thank you for watching, and please give it a like and subscribe.